just to introduce our next speaker. He's Bob Edwards from Research School of Computer Science at Australian National University. He's part of Machine Learning in Multi-Core Era project.
Yep.
Today's talking about a NetFPGA USB 2.0 interface for that project.
Do I use that microphone or this? Okay, thank you. So thanks for coming along, and also want to say thanks to the paper committee for selecting this paper out of very, very many. I hear a lot were turned down. When I put in my paper proposal, I put a couple in actually, but for this one I outlined a whole lot of different things I could talk about and said if you want me to talk about a particular aspect of the project in more detail to fit in with the theme of the conference or whatever, let me know, and they didn't. So I'm going to talk about the whole thing, which means I'm going to go a bit quickly and only touch on a few things, which I'd like to perhaps talk about a bit more if I had more time. So that's an overview. So I work with the Computer Systems Research Group in the Research School of Computer Science, which is just across the creek here on the other side of the Purple Pickle. And I've been there for, 13 years or so. I teach computer networking and also co-teach a free and open source software development course with Dr. Andrew Tridgell, otherwise known as Tridge at SAM.org, and also co-teach the operating systems course with Dr. Eric McCreath, who is not here, was going to be here. So do a bit of teaching, and the other half of my time I spend as a senior research engineer, and one of the things that our group's interested in is low power and low cost clustering, and we've been looking at building clusters out of system on chip or system on module machines based on ARM CPUs. And I guess the key one we've been looking at about a year ago when I started working on this project was the NVIDIA Tegra 2, which has now been superseded by the Tegra 3 and probably the Tegra 4 for all I know. But the Tegra 2 is the one I'm kind of more familiar with. And our idea is to build a cluster of these using common off-the-shelf or commodity off-the-shelf gigabit switches with Power over Ethernet, PoE. So the idea is to build little subclusters of systems on chips interconnected together with their USB, and then tie those back to ports on the gigabit switch over gigabit networking, which also will provide power to the ARM devices and their interconnect. And so that takes us to the USB 2 GigE switch, of which the thing I'm talking about today is a part. So first I want to talk very quickly about USB and networking. So we have lots of commercially available USB to network adapters available with Linux support, mainly 100 base TX, and there are some gigabit ones available as well. And inside Linux kernel there's a infrastructure called USB Net, which provides generic support across a whole range of these adapters. So about USB, it's a bus, usually a tree-shaped type bus, has one host and multiple peripheral devices, one or more, and the peripheral devices are joined to the host via hubs. The host is in control of all transfers, and it's it's not CSMA CD, but it's strictly one device is signalling at a time. So the host controls who gets to talk on the bus at any particular time. So it's not full duplex. USB 2.0 signals at up to 480 megabits per second, or at the lower speeds to be compatible with USB 1.1. That's 60 megabytes per second raw. In theory, you can possibly, if you really work hard, get 48 megabytes per second of real data across a single USB 2 channel if nothing else is there and if everything's optimised to max. On the other hand, 100 megabits Ethernet can transfer around 12 megabytes per second each way, full duplex. Gigabit Ethernet can do about 120 megabytes per second each way. So for a 100 megabits to USB 2 adapter, it's 100 megabit Ethernet, which becomes a bottleneck because its aggregate bandwidth is 24 megabytes per second, which is still less than the possible up to 48 megabytes per second of USB 2. When you go to a GigE adapter, the USB 2 becomes a bottleneck. USB 2, GigE can go significantly faster than USB 2. Which is why you mainly see 100 megabit adapters for USB 2. People say there's no point putting gigabit adapters in because you can't get gigabit out of USB 2. But my argument is the opposite, that you can actually do better than 100 megabit, so why not use gigabit? Because it's better than 100 megabit, you can get better bandwidth. Okay, well, USB 2 has a 125 microsecond microframe time, so the host or the controller polls all of the peripheral devices on its tree every microframe, every 125 microseconds. And so therefore, for a network interface, you've got an automatic 125 microsecond latency, because when a packet arrives in your USB network adapter, the host may not be coming around to poll for that packet or for that data from that device for up to 125 microseconds. So that's a bit of a bottleneck, causes performance issues. USB itself can transfer data in one of three modes: isochronous, bulk, or interrupt. Isochronous guarantees a certain amount of bandwidth, but it's up to 24 megabytes per second over USB 2. Interrupt is for very small packets like mouse or keyboard events, those sorts of things. And bulk basically allows you to transfer as much as you want in unused capacity on the bus. So if you've got one device that's using bulk, then it gets all the bus. And bulk is what you'd use for your USB storage devices, your flash device and your external hard drive, and it's also what most of the network adapters use. So they can basically use up all of the spare bus capacity as it's available. And so for each of these microframes over bulk, you can max out at about 6,000 bytes of data. Okay, Ethernet frames vary from 64 to 1522. I said 1522 because that's the max size of a standard frame with one VLAN tag on it, but these days people are putting 2 and 3 layers of VLAN tags in, so it might be a bit bigger than that even, but it's only 4 bytes each. For each VLAN tag it's only another 4 bytes, so it's not very significant. So therefore you can fit between 93 and 4 Ethernet frames per USB 2 microframe, depending on what size Ethernet frames you're using. And therefore, to make best use of your USB space or your microframe time, you want to pack multiple Ethernet frames, if possible, into each USB 2 microframe. So if you're only sending one Ethernet frame during each USB 2 microframe, you're not utilising your Ethernet or your USB to the max. And so there's various standards for doing that, and probably the one that's been adopted by the industry these days is called the Network Communications Model, or NCM, which allows chaining a whole lot of Ethernet frames together into one USB 2 bulk transfer per microframe. So that's just a bit of background about USB and networking. There's some issues to do with latency. There are issues to do with how to encapsulate multiple Ethernet frames into each USB frame, and there are issues to do with how you best join the different bandwidths together. So my proposal is to build a device that looks like a gigabit Ethernet switch on one side and has between 4 and 8 USB 2.0 peripheral device ports coming out the other side, and use the standard Ethernet learning switch fabric in between. So those who went to Radia's keynote on Tuesday will have learned a lot about Ethernet switching, and so I don't need to talk much more about that. If you didn't go to it, go and watch the video later. It was an excellent keynote. So USB 2, using the sorts of devices I'm using, we can get up to around about 41 megabytes a second bulk transfers. So it's a pretty good, having 4 of those 4 USB 2 interfaces feeding into a single GigE interface is a reasonably good impedance match. If the 4 USB ports were all transferring one direction at the same time to a destination at the other end of the gigabit Ethernet, then they would actually saturate the gig E. There would be some contention and some lost frames and whatnot. But that's a bit of a corner case, unlikely to occur. If you think of how a switch works, the USB 2 devices may actually be talking with each other, and therefore the traffic may not be going across the gig E, or there might be bidirectional traffic between the USB devices and the destinations at the other end. And so gig E is bidirectional, so it actually can do 240 megabytes per second in aggregate. And there's a picture which has not transferred across to my Mac version of LibreOffice. I'm sorry about that. I could probably draw it if I have time, which I probably don't. So think of a 48-port gigabit switch, category 6 patch lead coming out of that into a little box, and then 4 system on modules hanging around that, each one hooked up with USB 2. Okay, so the Gig 2 switch uses Power over Ethernet. The original Power over Ethernet standard calls for being able to deliver up to 15.4 watts at the port, and by the time you've hung that off 100 metres of Cat6 cable, with the resistance of the cable and stuff, the standard is supposed to guarantee that there's 12.95 or 13 watts of power available at the other end. We're not going to be using 100 metre cables, so you know, over a 1 metre cable, probably all of the 15.4 watts will be available. The Tegra 2 system of modules that we're looking at, which have a gigabyte of RAM on them, consume 2.5 watts each. So we're budgeting for 4 of those modules for 10 watts, and then there's 3 watts, between 3 and 5 watts left over for the switch fabric, which would be the gigabit network port itself, which is actually quite power hungry. Gigabit networking is generally uses a reasonable amount of power, just because of the voltages and signalling involved, and the switch fabric and the USB transceivers, of course. And so the intention is to realise that with an FPGA and some transceivers, a gigabit network transceiver and 4 USB 2 transceivers. We could also realise this with we could alternatively realise this with a 5-port gig switch you can buy down at Officeworks for $50, or off the net for a bit less, I guess, and then just hang a gigabit to net USB 2 adapter off 4 of those ports and have 1 port left over for the uplink and modify it for Power over Ethernet. That might work. The problem is that you've now got a total of 9 gigabit network ports to be powered instead of, well, actually, yeah, because you're powering all the system modules off the same Power over Ethernet, and so those 9 gigabit network ports are going to use a lot of power. So by doing it with a FPGA and the transceivers, we're hoping to save a lot of power by not having to transfer things into gigabit domain and back out again for each of the system on module devices. Okay, so that's where we got up to, and then we need a development platform in order to be able to realise this. And so I was also aware of the NetFPGA platform from other work I was doing. NetFPGA is a project from Stanford University. There's also a lot of work done on it from a bunch of researchers in Cambridge University. These days they talk about the keywords look for are open flow and software-defined routing are the sort of the big terms that are being used by these research groups when they talk about what they're doing and go looking for money. But NetFPGA is a set of hardware platforms that they've come up with. So there's 2 platforms that are currently being used. The NetFPGA 1G, which uses the Xilinx Vertex 2 Pro 50 FPGA, which has been deprecated by Xilinx some time ago. And that's what I've got here. So this is a NetFPGA 1G. There are 4 1G network ports over here. The Vertex 2 Pro FPGA underneath there. There's another FPGA just here, which is used for PCI interface, also a Xilinx device, and there's a Broadcom four-channel GigE transceiver chip. There's also some RAM, some dynamic RAM and some quasi-static RAM. There's 2 SATA ports over there. And the interesting thing also is this 40-pin 0.1-inch spacing connector at the top here, which is, most of the pins are connected directly to pins off the NetFPGA here. And that says, there's a little thing on it saying debug connector, or it says J4 actually, but elsewhere it says debug connector. And when I saw that, I thought, okay, maybe we can use that to do something interesting. So this project is about wire speed routing. Sorry, I'll switch back to my presentation. This project's about wire speed routing, switching, etc., filtering, doing all kinds of interesting network protocol stuff at wire speed. So NetFPGA 1G has PCI interface, 40-pin debug connector. Firmware is written in Verilog, and all reference designs and many contributor designs are fully open source using a BSD style license. So that's another reason why I chose this particular platform for coming up with the proof of concept for our switch. The second Xilinx FPGA, which manages the PCI interface, requires Xilinx IP, intellectual property. So there's a core that needs to be included in your designs if you actually want to modify what goes into that FPGA, which needs to be built against Xilinx's. You need to pay for access to their IP to do that. Pretty much everything on the other FPGA is open source. But the tools required to generate the bit files to the FPGAs are also proprietary, and they need licenses, and if you work at a university, that's not too hard. You get cheap prices and all that sort of stuff. In fact, this board, which you can't see, this board for a university customer is half the price of what it would cost for a commercial customer. So we pay something like $600 for it, but somebody else working in industry might have to pay twice that. So it's accessible to us, but we do still require some proprietary tools, which is a bit of a problem for me. There's a picture of the. There's a board. There's a board in a box. There's an FPGA showing the 4 1 gig interfaces and memory on the PCI bus to the host CPU. Over the other side is some software stuff. So they've got a reference router design, and a reference switch design, which was obviously the reference switch design was what was interesting for my project. And they've also got a GUI written in Java, which you can also click on to do stuff to interact with the router. Okay, I was trying to extract a picture of how this the reference design looks internally, but I couldn't get it, so I'm just going to quickly discuss it. There's a single 64-bit data path through the FPGA in their reference design, and so there's a multiplexer at one end of this data path which chooses packets coming in, or frames, Ethernet frames coming in from one of the 4 gigabit Macs, and then it processes those. The actual 64-bit data path has 8 bits of extra data attached to each data word, which tells you which channel you're talking about at any time. And the data flows through, and you can apply all kinds of filters or whatever inside the FPGA using a 125 megahertz clock. And so the packets generally move through fairly quickly, and you'll start seeing data coming out the other end not long after it's arrived at the input. It should be trivial to substitute some of the GigE Mac input outputs within the reference design for the USP Macs, or to actually just enhance it, and instead of having 4 inputs into the data path, having 6. So I decided to use NetFPGA 1G's development platform for building the initial USB 2 gigabit E-switch. And last year I also got to go to the NetFPGA Summer Camp 2012 and wearing a t-shirt. Sorry, interrupt any time for questions, by the way.
I don't quite understand where you're trying to get to with USB versus Ethernet switching. How are they how they're going to interact and how to
So getting closer to that, but
what's the purpose of the USB?
so this, okay, so the question is, why are we even bothering putting USB on a gigabit switch implementation? And I did miss some, thanks for asking that question, Martin, I did miss some key information. So these ARM system on chips are designed for mobile devices, and mobile devices rarely require a wide network interface, so they don't have them. They do have USB 2. So if you want to get data in and out of these low-cost, low-power ARM devices, you have a number of options, but USB 2 is probably the fastest option. Some of them have built-in Wi-Fi, but building a cluster out of Wi-Fi devices...
So if you were to draw your missing diagram, it would be a box with a chip, 4 USB ports fanning into a single gig port.
With a switch in between joining the, okay, so back up a bit. So these system on chips are running Linux. Linux has support for USB 2 networking, so these USB 2 devices are looking to the Linux kernels on the system on chips as if they were network interfaces. When packets arrive there, they enter the switch fabric on the NetFPGA in this case, as if they'd come off an Ethernet port, but in this case they've actually come across a USB link, which the kernel thinks is talking to a network port, but it's actually going straight into the switch without actually ever touching category 5 or category 6 cabling.
So yeah, the thing is USB 2 is the only practical interface to the system.
So some of them have PCIe as well, but when the idea first came up, USB 2 was basically what the common sort of, and certainly the Tegra 2 has PCIe as well, but USB 2 was the initial common sort of interconnect. And there's nothing about this design which is limiting it to systems on chips or anything else. You could plug a PC into a USB port and it would just come up as a device on the network as well.
That current board's got more than you need on it.
Yes. It's just I'm just using it as a development platform for the interface, so the interface is this little dude here.
The diagram you had before,
this is the actual interface we're talking about, and it just sits on top of that debug connector. And it has two, in this case it's got 2 USB ports. And yep, we'll talk about that in a moment. Is there another question? Bunny?
Just a quick question. Do you actually use the memory chips that are running the board?
So there's 2 types of memory, and one of them is being used as pseudo content addressable memory for the MAC address lookups for the switch fabric. So as the packets arrive, destination address needs to be looked up quickly in that memory using a hash function, all implemented with NetFPGA as part of their standard switch reference design. So I don't have to actually reproduce any of that. It's all open source, Verilog, ready to go. So all I'm doing is really feeding network packets in as if they've come across the Giga interfaces, but they're actually coming in through the USB 2. So with this summer camp I attended, we had to do a project, and one of the things that I learnt very early on is that there's this 64-bit data path or 8-byte data path. The frames arrive from Ethernet and just go straight through this data path. The first header in an Ethernet frame is the Ethernet header, which is generally 14 bytes, or it could be 18 if it's got VLAN tags. But it's not a multiple of 8. It's a multiple of 2. And so what that means is that all the data that comes after that is misaligned. So all of your, in particular, your source MAC address, your source IP address, destination IP address, all the things you require for routing and stuff, is all skewed across these 8-byte words that are going through. And so I thought, well, why don't we just add 2 bytes to the front of the frames before they arrive? So the Ethernet header now is magically 16 bytes with these two dummy bytes at the front. And then all of the IP frames and everything else was all now falling on the 8-byte boundaries. And so I spent most of the week implementing that at the max for the GigE, implementing it for the pseudo interfaces that come across the PCI, implementing this, updating the reference router and reference switch design so that they actually now don't have to muck around. There's lots of code in the reference switch design, to do with realigning data, which is coming through 8 bytes all skewed, and I could actually get rid of a lot of that code by just adding these extra 2 bytes to the front. And the 2 bytes are automatically removed when you get to the other end of the data path. Before the packets go back out to the output MACs, we take the 2 bytes back out again, so what goes back onto the MAC is just the actual Ethernet frame. So that was pretty good fun. They had never thought of it. I don't know why. It seemed pretty obvious to me straight away, but it worked. We didn't manage to do any metrics to see whether it made any difference to anything, but certainly it made the code look a lot simpler. The other NetFPGA, so I'm just doing a bit of a sidetrack into NetFPGAs away from my project for a moment. The 10G card will be the focus of this year's summer camp at Stanford University, and hopefully I might get to go to that as well. The 1G build infrastructure is all based on Python and Perl scripts. It can build the whole thing. It can run a whole lot of regression tests and do all sorts of stuff. Unfortunately, the 10G card is based on a Vertex 5 FPGA, and Xilinx don't support the same build tools, the command line driven build tools. This has been a major stumbling block for the NetFPGA project, and they've had to rely much more on the proprietary GUI based development environment, and they're sort of trying to move a lot of the code that was written for the 1G card across to this new environment for the 10G card. It's not really that new these days, it's a few years old, but it's hard for them to transfer it all across. The other thing is that the 10G card doesn't have the 40-pin debug connector on it, so it can't easily be used in the same way as a development platform. And I've got lots of ideas for projects to use on either of the boards, the 10G or the 1G boards. Excuse me. Wrong keyboard. Let's try this keyboard. Okay. Okay, so this little interface board, which I very briefly showed you, is what this talk's actually about. So it's just sitting on the debug connector. It's got 2 micro USB connectors, and then it's got these 2 Cypress Easy USB chips on it now. And there was you might have seen a lead which brings power. It needs 2.5 and 3.3 volts, neither of which come across USB interface. So the 2.5 volts and 3.3 volts come off the NetFPGA board, but they don't come through the debug connector. There's only 2 USB 2 interfaces, which is enough to do a ping pong test and stuff, but not to realise the full 4-port design which we want to get to. And we're up to version 2.5. Version 1 was a bit of a disaster. Version 1 uses Cypress USB 2 transceiver called a ULPI, Ultra USB 2 Low Pin Count interface, which is basically a serial interface engine. So this is the version 0.1 board, and I'll zoom closer in on that. So anyway, it's got those 2 little tiny surface mount chips there, which we soldered with a hot air gun. All the pins are underneath them. There's no pins, they're just ball grid type things, and the debug connector and the 2 USB interfaces. And I think Bunny touched on the problems with this during his talk. It basically relies on implementing most of the USB protocol stack in FPGA code. There are some implementations available, especially on the Open Cores website, the Open FPGA type work that people have been doing. But it was still going to be a huge amount of work implementing an interface using those serial interface engines and then putting all of the USB code into the FPGA. So we could have bought some IP cores for using with that, but we instead I decided at some point to go back and try a new design. So I reread the specifications for the Cypress FX2 LP, otherwise known as Easy USB devices. When I first read them, I realised it had an 8051 microcontroller, and I thought, well, that's just going to be a bottleneck. I didn't even read any further when I saw that. What I didn't read was that it actually has these FIFOs, and the main data paths can bypass the 8051 and go directly from the USB network and out some pins to whatever device comes next. And so fairly trivial to use those devices instead. And so the version 0.2 card has 2 of those. However, what I forgot was that the USB 2, the Easy USB chips use 3.3 volt logic, and the FPGA, I thought it was able to do 3.3 from previous work, but in fact it's been hardwired on this particular board to use 2.5 volt logic, and so it would have been dangerous to have actually turned it on. Not dangerous in the sense of causing anyone any harm, but it may have damaged the FPGA. So that board was a dud, and we went to version 0.3, put the missing level converters in, also reorganised the data paths, so instead of having a separate 8-bit data path for each of the 2 USB chips, we've now got a single 16-bit data path, and they share it. So whichever one's got data that's available can get it off the chip much quicker and into the FPGA. But you need to share. You have to share anyway because the data paths are bidirectional, so data going in one direction will have to be shared with data going the other direction on the same bus. Now I'm just sharing it 4 ways instead of 2 ways. And we clock the data through at 41.66 megahertz, which is the reference design's 125 megahertz clock divided by 3. And that gives us 83 megabytes per second aggregate across to the 2 USB 2 interfaces, which is plenty. The version 0.1 board was developed using Eagle. So I'm now cutting across to hardware design. This is what I was saying, this project involves lots of different aspects. So when I did the version 0.1 board, which is here, I used the popular Eagle software, which is free as in beer, but not free as in speech. And, you know, got that sorted out. We got the boards fabricated by Seed Studios Fusion service over in China, and they had some good information online about how to use Eagle to prepare the Gerber files and stuff for their service. But subsequently I used Getter on a different project I was working on. Getter is the GNU electronic design automation tool set. It's using a schematic capture program called GSChem and a PCB layout program called PCB, and it's sometimes called GAF, GSChem and Friends. So having used Getter on this other project, when I had to do the version 0.2 board, I decided to go back and use Getter for that instead of Eagle, because I felt uneasy using Eagle, and I love Getter. There are some anachronisms to using Getter. In particular, the key combinations you use to do panning and zooming in the schematic capture program are quite different to the key combinations you need to do panning and zooming in the PCB program. And so if you're switching back and forth, as you often do, you do a bit of layout and then realise you've got to change some pins in your schematic or whatever. You've got to keep switching your mindset from one set of key combinations to another, which is frustrating, but you get used to it. What's really nice is that both GSChem and PCB write easily understood ASCII text files. There's nothing hidden, it's not proprietary data formats like the Eagle programs use. And what's more, you can easily run scripts through these ASCII text files and like change drill sizes for all of the capacitors from 0.6 to 0.8 or something like that really easily. And I think you can actually do inside the GSChem programs and stuff as well, but I just got used to just quitting out of GSChem, running some scripts across the files, doing a bit of text editing with VI, whatever, and fixing things up that way, and then running it back up again to see that it was all good. With using GSChem and PCB, there's probably less library symbols available, so you need to lay out more library symbols of your own. I think even if you're using a program like Eagle, it's not a bad idea to use your own library symbols because you don't ever know for sure whether the ones that are coming in are as accurate as what you might need. That's my point of view anyway. So I did have to go and redo the footprints for some of the chips that I'm using because the ones that were available weren't quite what I wanted. Anyway, so I'm totally going to use Getter from now on. The other one I need to look at is KiCad, which is another fully open source electronic design tool. But if you want to talk to me about using Getter, GSCAM, PCB, etc. afterwards, I'm quite happy to talk about that at some more length. Okay, so looking at the software, there's basically three areas that need development. There's the kernel module to find the USB interface. There's the code that runs on the 8051 microcontroller on the Easy USB devices. And there's the Verilog code, which is, the Verilog code is by far the most complicated part of it for the NetFPGA. So looking at the Linux kernel module, so we're using Linux kernels. The trick is to make the USB network interface look like an existing supported USB network device. Not so much so that it actually mistakes it for a different one, but just use all the same code sort of base. I use the Axis drivers as the base for my driver, and in particular the AX88178, which is a gigabit network USB to interface. The Easy USB devices can boot firmware from one of three areas. Going back to Bunny's talk today, they actually have a little bit of firmware in them which you'd never get to touch, which can download the firmware for the 8051 either across the USB bus or from a EEPROM or a flash ROM chip. And if you put the right, if you have an EEPROM chip in there, you may not want to keep reflashing the code onto it all the time. So they've got this extra mode where if you put a particular byte sequence in the beginning of it, and then you can put your own custom USB manufacturer ID or vendor ID, I should say, and device ID in that, then the kernel, when you plug it in, will see that and run up the bootloader. The bootloader can then find the file on disk, download it across USB into the Easy USB device, and then the USB device can do a thing called renumeration. I think renumeration is a trademark. Yes, renumeration is a trademark, but it renumerates. I think I can say renumerates without saying trademark. Oh, here we go. So firmware, I've just said all that. Firmware can then renumerate the USB, so it basically shuts down USB and starts it up again, makes it look like you've just unplugged it and plugged it back in again, but now it's got a new vendor ID and device ID, and this time it should trigger the kernel to bring up the USB network device driver that you've loaded. So the code for the 8051 is developed using Small Devices C compiler, SDCC. It's different to GCC. It does some stuff differently, especially if you have strings and stuff that need to be pre-initialized. It actually goes and writes code that loads bytes into memory to initialize strings, which is just bizarre. I don't know why they don't just cut and copy stuff from the code space into the data space, but they actually write code that goes and puts the right values into the pre-initialized arrays. And stuff like that. It doesn't really matter because it only gets run once at boot time and then virtually does nothing else after it's initialized. All the rest of the data is passing directly through the FIFOs into the FPGA. But yeah, this SDCC is interesting. The Verilog code, it's intended to work within the NetFPGA reference design framework, specifically it's called the NF2, the NetFPGA 2 framework. Uses Python scripts for building and testing the Verilog, can simulate on a Linux host, so all their development was done on Fedora-based devices, and they have a complete simulation environment there. But it's again using proprietary Xilinx tools which do run on Linux. And then they have a synthesize environment to download the code across PCI onto the FPGA on the NetFPGA card. In order to do the simulation, I would have to build a model of the NetFPGA to USB 2 interface and get it all right in order to be able to do the simulations. And I'm trying to avoid that, so at the moment I'm just relying on synthesizing the designs, passing it down and using debugging techniques on the 8051 devices to see whether or not I'm getting the right responses. But I think maybe I might have to end up building those models and putting them into the simulation environment. Somebody tell me what the time is? I've still got a bit more. So the Vertex 2 chip has things called clock domains. There are 8 clock domains It uses one for its transmit clocks across all of the devices, so that's 125 megahertz clock. But for each of the receive MACs, so the 4 gigabit networks, each have their own receive MAC, and they have to be clocked separately because you can't guarantee what what the other end is doing in terms of pushing the data through. So there's 5 clocks of your 8 used up. Then there's a couple of clocks required for SATA, I think 1 for DRAM, or maybe it's 2 for DRAM and 1 for SATA. Anyway, there's no spare clocks available for my interface. So what I'm doing is I'm actually using the 125 megahertz clock and dividing that by 3 to give me a 41.66 megahertz clock for clocking the FIFOs. The FIFOs are allowed to be clocked up to 48 megahertz. So I'm losing a little bit there, but it's close enough that I'm not too worried about it. If I need it, I can take another clock away from one of the unused gigabit network ports.
Silly question.
Yeah, no silly question. Why does an FPGA have SATA on it?
Yeah.
They use SATA as a interconnect. If you want to have multiple FPGA cards in a computer, you can actually join them together with SATA and pass data between them really fast. Yeah. I have seen, so there's lots of contributed code in FPGA, and I have seen a couple of codes that use the SATA interface for doing that. I've never seen anyone use it for like storing data on something. But I suppose you could if you wanted to buffer pack, keep a log of stuff or whatever. You could perhaps squirt it straight out into a SATA device, but you'd have to build file systems and all sorts of stuff, wouldn't you? So my Verilog code, after it's got the clock right, the next thing it has to do is arbitrate between the 4 data sources, the 2 inputs and 2 outputs that are on those two USB interfaces, and multiplex all that data into this 64-bit data path. And again, it's going to add the 2-byte buffer, the 2-byte padding to the front, so that as the packets come in off USB and hit the NetFPGA switch reference framework, they'll all be lined up nicely. Using a round-robin scheduler, so just looks through which FIFO is ready to do something, and then moves all the data out of that. So there'd be a little bit of latency there, but not too much. I have it all modelled somewhere. The other thing that the Verilog code needs to do then is to deframe. So we have multiple, we can have up to 90 odd Ethernet frames packed into one USB 2 transfer. And so they need to be deframed once they hit the FPGA, because the FPGA is only dealing with Ethernet frames. So the Verilog code needs to be able to read through the chains of headers and take each Ethernet frame out and present them through to the FPGA, to the NetFPGA switch reference design one by one. And similarly, when there's frames coming through that need to go back, we need to repacketize those, and there's a bit of timing involved there to know just how many to repacketize. So there's a bit of work to be done there yet. It's not working yet, by the way, if you're wondering. It doesn't work yet. So I'm trying really hard to keep it all free and open. Here I am presenting on a Mac OS box. I apologise for that, but anyway. I'm trying really hard to use FOSS tools. Sometimes, for example, switching from Eagle to Gedda, there are people around our area who use Eagle who can help, but no one using Gedda. Actually, Eric arrived just a while ago and he's used it, so he can help. Yeah, so it's a bit of a cost. It's probably slowed down a bit the development process to use the FOSS tools, but I think at the end it's made for a much better design and something that's much easier to share with other people. So as long as FPGA synthesis tools remain the one area of proprietariness in the development environment, as well as the IP core for doing the PCI interface. And I'd love to talk to anyone who knows about open source FPGA synthesis tools. Maybe Bunny, do you know anything about that, or no? Yeah. And so almost there for a complete FOSS hardware FPGA development, but not quite. I need to gain some expertise in a wide range of areas. So I've, circuit design, which I've been doing for a long time. Verilog design, I've done it a while ago, but my brain sort of forgot a lot of it, so relearning a lot of there. getting up to speed on all of these Python build scripts and etc. Lots of things I've had to get expertise in. Project's not finished. Still more software to develop. And there's some links. And that is a very quick run through. Questions? Do you want the mic? Do you want to?
Do you think the open source community needs to build one of these USB UPL compatible cores so that projects like yours can use it?
I think the open source community needs to build lots of open source cores. So a PCI core would be a fantastic one to have. The NetFPGA used to use IP core for the Macs, for the gigabit networking, but someone from San Diego contributed, well, people working at the university there, contributed an open Mac for the Broadcom chip, which meant that we now have no proprietary IP on the main FPGA. It's all completely open. Every byte that's running on it is now open, but you still need the proprietary tools to compile them. So yeah, I mean, yeah, people should contribute their cores. So this, the whole culture of FPGA design seems to be around this whole idea of IP. It's built into the names. It's all called IP. So everywhere you go, it's all about somebody owns this design, and you need to pay them if you want to use it, sort of thing. And I really want to try and get away from that.
On the embedded micro side, the Tegra 3s or whatever, would you be using channel bonding on the Ethernet to actually, so you can get the performance out of your Ethernet interfaces? And also, if you're going to do that, you would need to make certain you use the right protocol on your Ethernet switch side to correctly load balance the packets across the link.
So I haven't thought about channel bonding at all. The intention is to have one USB port per Tegra CPU. Haven't actually considered whether you need more bandwidth. But as far as I know, the Tegra CPU's only got a single USB controller, so bonding the USB wouldn't get you anything. If you could bond it with some other interface that's available, you might get some extra. But the Tegra 2 itself only has a single USB channel. Luke.
So I wonder who this twit was who designed the NetFPGA board and didn't expose any power rails on the debug header. Whose idea was that?
So, well, I'd be really wary of calling any of the people in the FPGA team twits, but I've never seen anything that uses the debug connector. The debug connector is just there, and I've never seen a single reference to anyone do anything at all with it in terms of presenting information. So they may have used it internally just to check that things are working right, but it's got ground, so there's 6 ground pins. It's got 2 clocks, and it's got 32, or the 2 clocks that control the FPGA. They're called clocks, but I think they're no different to any other pin, and there's 32 other pins. I guess if you're debugging, you don't actually want the FPGA board to be powering the bug system. Yeah. Thank you.
So I may have kind of zoned out in some section. Is it possible to use this in like OpenFlow with booking over the USB for using the NetFPGA for like fast routing and fallback through the USB?
So question about OpenFlow, yes, you could certainly use OpenFlow on it once it's all working. There's no difference. As far as the rest of the framework is concerned, it will see no difference between packets arriving on the gigabit Macs and packets arriving on the USB Macs going through the demultiplexing process. These are the wires that were being referred to, by the way. These we're connected to 2 points on the board where there's 2.5 and 3.3 volts power.
So all the switching is in the FPGA. It's not Open vSwitch or any of that sort of stuff. This is all written from scratch in Verilog.
Yep.
All right, this will need to be the last question.
And full open source.
Just curious about the fact the compiler for the FPGA is proprietary. Is there anything inherently hard about that? Are the specs for the FPGA proprietary, or could somebody write a Verilog to Xilinx compiler and they just haven't?
So people have been discussing writing alternatives to. It's clear. I mean, Xilinx aren't the only FPGA supplier, and they all require you to use their own tools for developing the bit file, the synthesis tools. There's clearly information in those bit files which they're scared of their competitors finding. There's something in there which is going to reveal some trick they're doing inside their FPGAs or something which they're trying to keep for themselves. Because at the end of the day, they're selling the silicon. It's very hard for somebody else to sell their silicon. So I can't see what they've got to lose by making the specifications, the bit files completely open. But clearly they feel that if they did that, they would lose something. I'm not sure what. But there's all sorts of cleverness going on. There's like some of these IP cores, they will automatically disable themselves after so many hours of use. So there's obviously things going inside the FPGA which can time how long a particular core's been running for and then turn it off. And it's like, you know, there's all this built-in designed for, you know, what's that? What's that website? Anyway, bad design type stuff. Where it's not in your favourites.
We're out of time.
Everybody's fine design as well.
We're out of time, so we'll just please thank Robert for giving a speech today. On behalf of LCA, I'd just like to present you.